where we developed a TOW performance system. And I will talk about accelerating AI applications, evaluating the performance of your applications, figuring out why your application is taking so much time, and how you can find ways to optimize your applications. So there are 5 stages of AI deep learning, as you know, from data collection all the way to action. And this involves getting the data from images and video, text, voice and sound, sensors, and then analyzing that. And there are various stages in this 5-stage process where you can see that you have a large amount of data coming in from the raw sources. I must credit this slide to Ulrich Walter from IBM for these 3 slides. And you can see that as you go down to this side, you're reducing the amount of data and you're gaining better resolution, better knowledge about what it represents. So you analyze and prepare the data, then you have to go through the information to knowledge by learning, and then reason and conclude what that data provides you. And you can see this in this, that there are many challenges. There are many challenges to processing this large amount of data. As you collect it, prepare it, analyze it, learn from it, and inference, you see the volume going from terabytes to petabytes to exabytes. And you have to finally look at what knowledge you can derive from this and how long it takes you for each of those stages. You have to make different choices regarding the hardware, regarding the GPUs, the latency, and at each stage, if you have precise measurements to guide those decisions, you will be able to make informed choices. Many times people just run their workflow with no knowledge about what those phases, how long each of those phases takes, and what parameters are critical for each phase. So instead of looking at total wall clock times, we will show you tools that can help you analyze where the application is spending its time and what choices you can make, both in terms of hardware and software, to improve that workflow. So these are the stages that are described here, with the data collection, processing, learning, and finally the inference. And you can see that in many cases, when you choose the hardware, whether it's a question of processing a large number of queries, as we heard, on a database in a GPU, or looking at, as in the previous talk, using FPGAs, and bandwidth and latency are very important factors in this. The time it takes to move the data from the CPU to the GPU or to the other accelerator device, the links that connect the CPU and GPU, you should be able to look at the full system and say, what parts are executing on my CPU? Where does the I/O take place? What file system is being used? Can I accelerate that by using a non-volatile memory, a high bandwidth memory component? Where is it fetching the data from? How long does it take for the kernels to run on the GPU? What is the transfer rates for I/O? How much memory is being used? These are all relevant questions as you decide the platform that you use for running your workflow. So with this, I would like to present the TOW performance system. I've been working on this project for about 24 years now. The tuning and analysis utilities, or TOW, comes from the University of Oregon, and our goal is to provide this profiling and tracing toolkit on all the HPC platforms that we all use. Our goal is to provide integrated instrumentation, measurement, and analysis framework. TOW is widely ported performance evaluation system. It also provides a full performance data management and data mining toolkit. And most of all, it is available in a BSD style license. There are no licensing costs. You can use it on as many nodes as you would like. It integrates well with application frameworks. Our focus has been on HPC because primarily our funding comes from the HPC community, but we have been looking at AI frameworks because a lot of workloads are being run on these HPC systems, as you will see in the next talk presented by Thorsten. And we have support for adding hooks to your program, instrumentation for languages like C, C++, Fortran, and Python. We can transparently add hooks to your Python codes, as we will see. And you can see the components of your AI workflow, which includes time spent in individual Python routines and the Python to C interface, and how much time is being spent in C routines for system calls and all. We also support other languages. We have support for parsing the source code as well for traditional languages like C, C++, Fortran. We can intercept runtime calls with well-defined interfaces like the MPI library, POSIX.io, and so on. We can add hooks using static or dynamic linking, and we support preloading of shared objects. This allows us to actually take an unmodified binary, and run it with our hooks inserted in it with no changes. We can also rewrite binaries, and we have frameworks like Dynenst API from University of Wisconsin and University of Maryland that help us do that. But once those hooks are inserted, you can see that it calls the measurement API for profiling or tracing, and then generates performance data which can be analyzed in our tools like Paraprof and Perf Explorer. So you're wondering, what can Tau show me? Well, Tau can show you how much time was spent in which code region, at the level of routines, at the level of files, at the level of loops. And also we can drill down to individual statements using event-based sampling. So what is the time spent in OpenMP loops, the execution of time on the kernels that execute on the GPU or on the FPGA? We can intercept the time, we can intercept the runtime system calls like OpenCL and see exactly how much time was being spent on the FPGA or on the GPU. And the best part is Tau is built in a modular way, so you can see the time spent in different runtime components like the pthread interface, the IO subsystem, the CUDA components, or the OpenCL components that execute on the GPUs. Instead of instructions, you can also look at the hardware performance counters. These microprocessors have low-level counters that can track how many instructions were executed, how many vector instructions were executed, how many scalar instructions were executed. They can see floating point instructions, level 1, level 2, data cache misses, how many cycles the CPU was idle, waiting for data to come. You could pinpoint in a loop how many floating point instructions were executed and divided by the number of level 1 data cache misses. So you could see precisely how many instructions were executed that were useful with respect to the data cache misses. Like if you were asking yourself, well, this is the loop that takes the most time. It takes 65% of my code execution time. Now, how many cycles was the CPU idle in this loop? How many floating point instructions did I execute before I had to go off and fetch data from the level 1 data cache? Was it 2,000 floating point instructions? Was it 64 floating point instructions? Was it 2? Your code could be doing very different things. You could see how it accesses the memory. The way the arrays are laid out in memory, do they correspond to the way you are accessing the memory? Otherwise, you're wasting a lot of performance, and just changing a few things can change the full profile of your application. You may be interested in seeing what is the memory usage of my code. When and where was memory allocated and deallocated? Were there any memory leaks? Did I access arrays past the bounds of the allocated memory? If I allocated a 1024 byte array and I accessed an element at 1040, can anyone guess what will happen? Likely nothing at that point. The code will continue execution. And then later, it will crash in a completely unrelated place. And as you look through the debugger and you try to say, well, this is a very reasonable thing that I'm doing where it crashed, you may need tools to help analyze what happens to your memory. You may need to find out exactly where you exceeded the bounds of the page that was allocated. So there are tools like that that are integrated in TOW. You can see what is the high water mark for your memory allocation. So if you're wondering where your memory goes up and down, what is the max it ever reached in the kernel? You can set an environment variable in TOW, and it will show you precisely what is the peak memory usage. You can also assess the energy usage in your code. You can look at the I/O characteristics. Very simply, you are processing a lot of data. You may want to know which files did my code access. What file systems were they on? Was it on a Lustre file system? Could I move that really large file and see what is the volume of data? What is the bandwidth that I observe for read and write operations? And if you find, you run the code through a profiler and you see that 80% of the time was spent accessing a file, a really large file on a shared file system. And you said, well, this system has NVMe, which has a really high bandwidth. And you take the file and move it to, say, a RAM disk or the non-volatile memory, and the access time can reduce dramatically. Especially, this is important for some codes where you may be having one rank read the entire file and then broadcast it to other constituents, and when everyone is waiting, the time just multiplies. So reducing the access time for those files can make a huge difference. A profile will show you exactly how much data was transferred, when it was transferred, who did the transfers, and what bandwidth you observe for read and write. You may want to see how your application scales. Yes?
Typically, actually, as a performance monitors take also some, let's say, performance of the system itself. So how do you see the overload or the overhead of how then in comparison to the payload of the system?
So there are ways to even compensate for the instrumentation overhead of a given tool. We have a flag called compensate that can assess with a tight loop how much time a tool perturbation can add. But when you're looking at the cost of, say, half a microsecond for access to a timer versus 3 seconds for some big operation on I/O, the time is negligible, and you don't need to eliminate that. But there are ways. That's a very good question. If you instrument at a very fine granularity and you execute a tight loop over billions of times, then TOW has a built-in throttling mechanism where it looks at how many times a function is called. If it's called over 100,000 times, it says, was it executed at least 10 microseconds per call or more? If not, let me just throttle it away and disable the instrumentation so the subsequent calls don't access the system clock. And so it can just speed up, and you can change those throttling thresholds. Yes?
It's related to this, so especially when you do, for example, GPU profiling, some profiling tools put in like synchronization hooks or whatever,
yes,
which then basically artificially inflate the runtime because something which was previously overlapping doesn't overlap anymore because of the synchronization. So what does TOW do for these things?
So I have not seen synchronization hooks explicitly inserted by TOW. If they occur in the runtime, those calls are then instrumented by instrumentation of the libcuda, and then you can see whether it's libcuda or Rockham, you can see the exact time spent in synchronization and when and where it takes place. So
yeah, we had like, I think we had like a, it was an HPC application which we profiled, and there was like profiling books like from that application.
yes.
And the guy who wrote this profiling books for this application, they put in like, once you enable it, they put in like device or like group synchronized on threads, and that basically destroys like distorts the profile in the end, right? So, but you say Tau doesn't have this.
Tau does not have that, but I should qualify that and say that where there are like threads involved or at the end of the execution, you typically need to have a join operation so that you can write out the profile file in a consistent manner. So at the finalized time, there can be some time for the join to take place for the CUDA thread join. But other than that, it should not have any problem with that. So the phases for instrumentation include source instrumentation for traditional languages like C, C++, Fortran, where you can use a framework in Tau called the Program Database Framework Toolkit that parses the source code, and using the internal representation, you can add hooks to your source code, a copy of the source code, and you can also use the selective instrumentation filter file to reduce the runtime overhead of what you're instrumenting. You have support for compiler-based instrumentation where hooks are added to your application code by the compiler directly during the compilation of the process. And we have files like taucc and tauf90.sh, which can be used to compile your code when you're using compiler-based instrumentation. But what is of interest here is we have Tau's runtime preloading using a dynamic shared object where you can just, instead of running .app, you can say tauexec.app or taupython app.py. And there, without any changes to your binary, Tau launches the application, preloads the Tau shared object. So in the memory, when the memory is clean, the Tau library comes in. It defines certain hooks for runtime library instrumentation and all, and then the application is brought in. So the application's calls to the library are intercepted by Tau, and application calls Tau, which starts and stops timers, and then calls the runtime library routine. It can generate profiles and traces. Profiles show you how much total time was spent in a routine or a region of code. Okay, the total time. So if there was a write function and it was called 10,000 times, at the end of the program, it will say 50 seconds were spent in the write function over all 10,000 invocations. Whereas tracing will show you for each thread of execution when the entry and exit for each of those 10,000 calls for write take place. So you can see exactly what each process was doing. Yes?
Does it also give you some hints or maybe some recommendations for compiler flags later on when you execute this code that you can say, well, for that type of compile, you might actually add a certain switch for getting better?
So we have a plugin framework where we can analyze the profiles and look at certain runtime characteristics and give recommendations. And for most cases, we assume that you start with a good set of compiler options like O3 and QHOT or so, and then get the best performance you can, and then profile it with all the optimizations enabled. But we do have that capability of looking at, for example, looking at a profile and saying that you are spending a lot of time in reduction operation. And this reduction is being done in this runtime library. Instead, if you were to use the Mellanox Sharp interface and do the collective operations in hardware at the network interface card, it will reduce a lot of your time. So you can offload that capability of collective operations to the hardware directly. And it can give you those kind of recommendations. I'll show you a small example of that. But just to get the terminology straight, if this is a function that takes say 100 seconds and it calls a instrumented function where there are start and stop hooks added, a function called bar, which takes 20 seconds, then you'll say that this green part is the inclusive time, or 100 seconds, and the orange part is the exclusive time, or 80 seconds. So that's the exclusive contribution. You typically have probes that start and stop and define a particular region for direct instrumentation. And this is used for tracking I/O calls, tracking all the POSIX calls, MPI calls, pthread calls, CUDA calls. Now you can also use sampling, where you don't need to modify the code, and you can just get a periodic interrupt, and based on that interrupt, you can say that the time spent in this region was so much. It's a very simple way, but it can look through layers of runtime libraries without changes. And you can see how much time was being spent. So in sampling, you get a periodic sample like this, generated from a system clock or with the overflow of hardware performance counters, where you can see how many samples you collect. So just to go by with a simple example, if my application took 100 seconds and say we had 100 samples, 1 per second, and there was one region of code that collected 30 samples, I'll say that 30% of the time, or 30 seconds, were spent in that particular region. So it just does that, while instrumentation requires an explicit start and stop call, and then you can generate precise results as long as the instrumentation is coarse-grained. You see, if your timer takes half a microsecond to execute, then you should not be measuring something that takes 20 nanoseconds with it. But if you measure something that takes 30 milliseconds, then you will have no problem. So this is the tool TOWExec that can track the time spent in MPI, CUDA, OpenACC, pthread, OpenCL. And so this can be used with FPGAs as well as GPUs. And you can see the time spent in OpenMP, POSIX I/O, memory, and you don't need to modify the code at all. You can also enable other advanced options of TOW, like this. So if I have a code which is run with a.out, I can just say TOWexec-OpenCL a.out, and then the FPGA execution will be highlighted. You can say OpenACC or ROCm or CUPT for CUDA profiling tools interface for CUDA calls. You can do OpenMP TR6 instrumentation. It's just a new standard that we are tracking. And then you can track I/O calls like this, enable pthreads. You can look at event-based sampling like this. You can also specify a hardware performance counter. So instead of saying every 30 milliseconds take a sample, you could say when 100,000 data cache misses take place, please interrupt the program, like that. You can also specify whether you want to sample with a coarse-grained file resolution or a line resolution or a function resolution. So this is an example of using tags in TOW for configuring TOW with different packages. If you configure it with a package called PAPI for hardware performance counters, you can enable the -T PAPI flag, and it will load this shared object located over here, like this. Once you load the performance data in TOW's paraprof tool, it looks like this. It shows you all the ranks over here for MPI or the host-based processes, and then within that you can see the individual threads of the GPU. But when you go here and you turn on the stack bars together, you can see all of these functions line up in their own space. And then TOW supports a 3D profile browser. So you can see all the functions along one axis, you can see the MPI ranks along another axis, and the height can be the exclusive time spent in the application function. What this allows you to do is it allows you to see the shape. It shows you the shape of the entire execution, and you can use the crosshairs to go down over here and say what was that function, on what thread did it execute, and how long did it take. Here you can see a step function between the threads, and you can see that the time spent in different code regions was decreasing with different ranks. You can see such patterns using TOW. Here's an example of using the MNIST data set on a IBM Power AI system. This is located at Barcelona Supercomputing Center, and it's using the Power AI software stack from IBM. So I can just source this TensorFlow activate, and if this is how I execute the program, which is Python, classify this .py with this data set, then all I need to change is change the Python to tau_Python, and then specify the kubti flag, and then use the same Python file with the same data set, and then launch Paraprof. So I did not need to change the Python files. I did not need to change the Python interpreter. I did not need to change anything else in the data sets. With no changes, you can just launch Paraprof like this, and it works with this. It brings up the first window that shows you the Paraprof profile manager that says this is a Power 9 system, Ultivate supported. You can see there is a GPU name of V100 XM2 16 GB GPU, compute capabilities, the clock rate, the memory bandwidth, all the characteristics of the IBM Power 9 GPU system. Then you can go down to the context event windows that show you the max, min, mean values for individual allocations. You can see the events and see how many events took place on which thread, the GPU occupancy in warps. You can see the local memory, the data transfers. So essentially, you can see how much data moved between the host and the GPU. You can see the names of the kernels that executed on the GPU. You can see the actual names of the events that took place on the GPU. This is the tensor assign operation in the eigen meta kernel. And you can see the exact C++ name of the functions. You can see down to the kernel names as they execute on different threads. And you see here is the GPU time for different events of TensorFlow. And this is all running on the IBM system. You can see the time spent in the CUDA functions. And see the names of the Python files, the functions in Python, as well as when Python calls C functions like read, fork, stat, append, it shows you the Python C boundary without any changes to your Python code. You can also see along the data transfers, you can see bytes copied from host to device along which Python call path. So you can see that TensorFlow called these functions. There's a call tf session run, which calls tf session run wrapper, which then calls a CUDA mem copy host to device asynchronous. You can see how many transfers took place, what was the max bytes, what was the min bytes, total bytes copied, along which call path. So that level of detail is exposed by this tool on a per thread basis, and you can see all the CUDA runtime calls. So you can answer questions like, how much time did my code take in synchronization operations with CUDA? Okay. Was there so much congestion between the link between the host and the GPU that I need to go through a much faster connection between a CPU and a GPU? Is PCI Express bus really a bottleneck? And how can I use some hardware that overrides that bottleneck? Okay, so those questions are questions that you may want to ask when you're profiling your application. Here we see the time spent in different CUDA library functions. Even if they strip out the debugging symbol information, we can still see which library was executing and how much time it took for each of those pthread or CUDA library functions, and how much time was spent in pthread libraries for mutex locks and unlock operations. Here is another example of a data set for Caffe GoogleNet, and this is the Caffe code using again Power AI software stack, and you can profile it with no changes to the application binary. You are just using event-based sampling with unmodified code on production hardware. Now there is a lot of interesting research that our group is involved in, and one of that is, can we build a bridge between runtime layers and tools? Can we tune the runtime ourselves? So MPI is one of the targets which provides a tool interface called the MPI Tools Interface, which allows tools to communicate with MPI, observe the performance at the low level, hardware level, and then change the control variables exposed by MPI. So for example, if you have a high-speed network interface, say a Mellanox EDR card, and packets are lining up at that interface, and you want to say your application is sending more data than can be flushed out from the interface card, and you're maintaining a buffer of those packets that need to be flushed out. You may want to know what is the queue length of that buffer. Is it 2 bytes, 2 packets waiting to be flushed out? Is it 200 packets waiting to be flushed out? Is it 200,000 packets waiting to be flushed out at the network card? Is it red hot with congestion? So what the application can do is it's sending out the data to be sent out to the different nodes. The runtime layer can communicate this information to the tool, like tau, and then tau can change the various parameters at runtime, moving some operations, like collective operations, directly into the hardware so that they are done at the Mellanox sharp fabric level instead of doing it in software at the application runtime level. So we have this mechanism for using auto-tuning plugins, and then tau can get all the events where the runtime tells it what's happening right now, and then tau can be used to evaluate that and make recommendations as well as change values of critical parameters and tune the runtime like this. This is joint work with the Ohio State University, the MVAPICH team. And you can see that the pressure on the system, where red is the pressure on the MPI communication layer and green is the rest of the application. This is shown in Vampire from TU Dresden in Germany. And you can see now that after tuning the code, your application the green has increased considerably and the MPI time has reduced just by making those switches. So the idea here is that there are knobs that you can turn. There are knobs in the runtime. But when you install the software, the runtime layer, and it has 400 different knobs, it's hard for a user to manually figure out which knobs to turn. But once you make measurements, you can find out which knobs are relevant and then change those at runtime using a plugin approach. So here you can reduce the total execution time considerably. This is the program database toolkit for static analysis of code written in C, C++, and Fortran. And it allows us to build tools like the tau instrumenter, which can read the application source code and add hooks to an instrumented copy. So you can automate the process of instrumentation even at the source level if you want to add hooks in some code segment. You can give it an instrumentation specification file that tells you what to instrument, what not to instrument, or how deep the instrumentation should be at the loop level. And then you can instrument the code and then analyze it. This is a profile from a code called Fun3D. It comes from NASA Langley. It's a CFD code. And you can see that the time spent in different code regions and the MPI ranks, it's not uniform. There are these valleys. And you can see the shape and go down to a particular function and say, look at this MPI bcast on thread 19, which was taking 7.4 seconds right here. So why is that taking a little longer? Why is it not uniform? Are questions that you can explore and look at the full profile and see what each rank was doing. You can drill down along a calling path with appropriate instrumentation and say, what exactly was this code executing. And you can see that it was executing, say, this 0.5 solver, which came from this call to the single matrix complete transfer, which came from this call graph, so to say. So you can see the edge in a call graph and see which components called which other code regions and how much time was spent in that across all the ranks, across all the nodes, and you can see the profile for the solver. Now there are many different runtime parameters that you can set to generate this data, like call path profiling, tracking the memory footprint, looking at the power, or sampling, or even turning on the signals. If your code crashes, and you just want to find out where did it crash on each node, you can just run it with tau exec a.out and turn on this tau track signals to 1. It will give you a full call stack. It shows you exactly what each rank was doing when it crashed, and what was the performance of the code until that point of failure. So although tau is not a traditional debugging tool, there are some things in tau that can be used for debugging, including support for tracking memory operations. You can even track the load on the system. You can specify code regions to instrument. You can generate trace files and look at a range of memory leaks and other data for memory analysis of your code with no changes to your application. So the tau software is available from tau.uoregon.edu. We also have a virtualization appliance that's available. It's an OVA file where all the tools are pre-installed for you. We also have a new project called the Exascale Scientific Software Stack, where we are assembling a range of tools in a container environment, including tau. This is where the research goes on. My office is located here in the Performance Research Lab at the University of Oregon. We have a very active visitor program. Many people come and visit us for a couple of days, and if you would like to look at your code with us, you're most welcome to come and spend some time with us in Eugene. It's beautiful in the spring and summer, not so much in the winter. And I would like to thank our sponsors, the US Department of Energy, the Exascale Computing Project, the Office of Science, Lawrence Berkeley National Labs, Livermore, Los Alamos, Sandia Tri-Labs, the Battelle PNNL Oak Ridge National Labs, the Department of Defense, the National Science Foundation, NASA, the CEA in France for sponsoring this project, IBM for their equipment and support. I would like to thank our partners at the Ohio State University, Paratools Inc., University of Tennessee, Knoxville, the developers of PAPI, TU Dresden in Germany, the developers of Vampire, and Jülich Supercomputing Center, the developers of tools such as Scorpy, Scalaska, and Opari that are working with tau. So thank you. Any questions?
Just a question. The last two ones, are they used?